My name's Jen Beverly, and I lead the Wildfire Analytics Research Team at the University of Alberta. Today I'm going to talk about 3 projects where we're using photos to characterize fuels. Team members who have contributed to this work include Hilary Cameron, Andrew Stack, Ashwat Sharma, and Jared Randall. Now we've been looking at different kinds of photos, hemispherical, downward facing, as well as photos taken during operational overflights. Before I get into the projects, I'd like to acknowledge our research collaborators, Gaston Diaz, Martin Barzik, and Prannoy Panda, as well as key contributors from Alberta Agriculture and Forestry, Dave Schroeder, and the Alberta Wildland Fuels Inventory Program, CRUISE. And finally, our funding has been provided by Alberta Agriculture and Forestry through the Canadian Partnership for Wildland Fire Science. Now, field sampling is costly, it's time-consuming, and resource-intensive. It's not surprising that people have asked, is there an easier way to get rapid estimates in the field? If there were, it would enable documentation of fuel structure and fuel loads in a much broader range of settings and situations. Now, rapid fuel load estimation with photographs is well established. People have been doing it for a really long time. And there's programs like the photo load sampling technique developed by Bob Keane and others in the US that are widely used to estimate fuel loads based on matching photos. There's also been a lot of photo guide development in different situations using hemispherical photography and other photographic methods, as well as the photo load method in Canada and in Canadian fuel types. Now, one of the questions we had is what kind of new technologies might enable expanded use of photo-based assessment of fuels. In particular, we were interested in whether or not some protocols could be developed for documenting fuels in more operational settings, where there wouldn't be the same capacity to document and conduct photo-based assessments in the rigorous way that they might be done in a research or an experimental burning situation, for example. Now, there was a recent paper by Bianchi that had looked at comparing smartphones for hemispherical photography to more traditional professional photographic methods, and found that actually smartphones performed quite well. And I thought, well, that's encouraging. Let's give it a try. Now, we didn't use the same equipment that Bianchi used. We used an iPhone 7, and we used an Olo clip fisheye lens attachment to do the hemispherical photos, following the same basic method that Bianchi had used. You take 2 perpendicular photos at a location and you can patch them together to make a complete hemispherical photo for assessing that gap fraction, the amount of sky that's coming through. Now, the data collection was done by Alberta Wildland Fuels Inventory Crews with some logistical support and training from Andrew Stack. And we really did use a relaxed protocol, which meant we ignored almost all the rules around taking hemispherical photos, and just asked the photographer to hold the camera level at eye level and to snap the photo, rotate it so it was perpendicular in the second photo, and that was it. Now, Hilary Cameron's been analyzing the data in collaboration with Gaston Diaz, who's an expert in this kind of hemispherical photography, and in particular in analyzing these photos when they're taken under imperfect conditions, like our photos. And the results are pretty encouraging. So this is just showing the statistical relationship between canopy openness documented with our imperfect hemispherical photos taken with smartphones in relation to canopy fuel load that was measured by the OFIP crews at the same plot. So yeah, pretty good relationship from just 8 photos. Now, the other thing we had the crews do, since they were there taking the hemispherical photos, is to take that fisheye lens off and then just point the camera down and snap some downward facing photos. And you can see there was just a wide variety of different surface fuel conditions. And we then had a technician manually classify the surface cover type in the photos. And Hilary Cameron has been analyzing the relationship between the technician's analysis of that sort of fuel type cover versus the field data. And it's turning out not too badly, considering that these photographs, again, taken with very relaxed protocols, and in comparison, though, with the the ground cover percentages estimated from the OFIP crews using the more intensive field sampling techniques, the relationships aren't bad for some of the cover types. For others, they don't look so great, but I'm just going to show you the good ones. And of course, it's pretty time consuming for a technician to go and basically paint the photo, characterizing the cover types in the photo to do this kind of analysis. And so the natural question was, could it be automated? And so Martin Barsic and Pranoy Pandey have helped us out. And Pranoy has been using the manually painted photos, the manually classified photos, to train a computer to automate the process using a supervised learning-based deep convolutional neural network, and they're performing what's called image segmentation. And so these photos just show you an example. The original photo, the manually classified photo in the middle that was done by our technician, and then the machine classified version of that after Pranoy had developed his algorithm. And now the last project I wanted to talk about where we're using photos is the Overflight photos from operational initial attack. So these photos are taken when fires are reported. Crews go out and the fire is assessed, a photograph is taken, and there's a lot of detailed information about what's going on at that time, which makes it a sort of a really interesting situation for analysis. And when you look at these photos, and many of them provide really good indication of the fuel conditions, and not just the fuel type, but the structure of the canopy fuels in particular. So this is work that's being conducted by Andrew Stack as part of his MSc thesis research, and he has limited his analysis to fires burning in black spruce fuels at the time of that initial assessment. And so we're matching the assessment with the photographs with the outcome of the fire. Now, Andrew's done a lot of modeling, and he's about to wrap up his thesis, so there will soon be a full-length presentation by him of what he's done. But just a little sneak preview. This is one of the models he wanted to show. So this is showing the probability of a fire in black spruce escaping initial attack as a function of smoke color, relative humidity, and forest structure at the time of assessment. And for structure, he's just looking at two classes, closed versus open, which he estimated based on the photographs. And then he also extracted other variables from the photos, like the color of the smoke, which is a good indicator of intensity. And so you can see that when you've got that higher intensity fire and the relative humidity is dropping, there is quite a difference in the probability of escape depending on stand structure. So it's kind of a neat insight using just operational photos. Okay, so as a summary, what are the questions we're asking about fuel characterization? Well, one of the questions we wonder about is what level of detail and precision is necessary. If you can get 80% there with 5% of the effort, is that good enough? And maybe that makes it a useful method. Are we fully exploiting simple, accessible, understandable, fast, and expensive, what I'm calling SOFI methods? And then, of course, what insights about fuels and fire behavior can be gained by readily available data and documentation captured during suppression operations? So thank you for listening. That's our website, wildfireanalytics.org, and you can follow us on Twitter @fireanalytics.